Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into embodied AI agents and how they're modeling the world.
Exciting topic. It feels like we're really starting to see some momentum in this area. Embodiment has always been a bit of a holy grail, right? Getting AI out of the abstract and into something tangible.
It's certainly a hot area, but I'm still not entirely convinced that embodiment alone is the solution. There's a lot of hype, but are we truly seeing a leap in understanding? Or just more sophisticated simulations?
I think it's a necessary step, Sarah. We're seeing impressive results in domains like robotics, but I agree that embodiment alone isn't sufficient for AGI. It's a component, and I think a very important one for grounding the models.
Grounding, exactly. That's the key term. It's about bridging the gap between abstract symbols and real-world experiences. And I think that's why the research I've been reading on how sensory inputs shape human cognition is so relevant.
Absolutely. Think about how a baby learns. They don't just passively absorb information, they actively explore their environment, manipulating objects, experiencing different textures and temperatures. That sensory feedback is crucial for building an understanding of the world.
But how do you translate that into an AI? Simply feeding a robot visual data and motor commands isn't the same as genuine understanding. Where is the symbolic representation? Where is the abstraction? A baby learns hot from a stove, but then can apply that to other situations. Does the robot just avoid that one stove?
That's where I think the ability to translate between different coordinate representations comes in. The robot doesn't just need to learn to avoid that stove, it needs to understand the underlying concept of heat and how it relates to other objects and experiences. It needs to map from, say, a thermal image to a symbolic representation of danger.
Right, and that translation, that mapping is incredibly complex. We're talking about integrating sensory data, motor control, and abstract reasoning. It's not just about building a better robot, it's about understanding how the brain itself works. I've been looking at research on brain plasticity and how the brain is constantly reorganizing itself based on experience. Can we mimic that dynamism in AI architectures?
I think deep learning offers a path forward there, even if it's not the only path. The ability of neural networks to learn complex mappings from high-dimensional data is undeniable. And with enough data, they can start to extract those underlying relationships that you're talking about, Donald. Think about image recognition. A network can learn to identify a cat in any orientation, lighting condition, or background.
Yes, but that's pattern recognition, not understanding. A neural network can tell you it's a cat, but it doesn't know what a cat is. It doesn't understand the concept of catness. It doesn't know that a cat is a mammal, that it meows, that it hunts mice. And that's where symbolic reasoning comes in. We need AI that can reason about the world, not just classify it.
Exactly. It's correlative and not causative. You can give it millions of pictures of cats, and it will eventually learn to recognize one, but it won't understand the underlying principles. And that's why I'm so interested in this spatiotemporal aspect. It's not just about recognizing objects, it's about understanding how they interact with each other in space and time. A cat chasing a mouse, that's a dynamic interaction that requires a different kind of understanding.
So how do we build AI that can capture that dynamic interaction? I've been thinking about the role of embodied cognition. Could incorporating physical interaction and sensory experiences in machine learning lead to deeper, more nuanced understanding? Like imagine AI that learns to play soccer, not by watching videos, but by actually playing the game, interacting with the ball and other players in a physical environment.
That's a fascinating idea. And we're seeing that to some extent with reinforcement learning and robotics. Robots are learning to perform complex tasks like grasping objects or navigating obstacle courses through trial and error. The key is to design the right reward function that encourages the desired behavior. You can train a robot to walk just by rewarding forward progress.
But again, that feels like a brute force approach. You're essentially handcrafting the solution by designing the reward function. What if the environment changes? What if the robot encounters a situation it hasn't been trained for? It'll likely fail. We need AI that can adapt and generalize, not just perform well in a specific, predefined environment. Like, if the reward function is to score a goal, it might cheat if that's the easiest way, even if the rules say not to.
Yes, the reward function can over-optimize for the wrong thing. It's not about blindly pursuing a reward. It's about understanding the underlying structure of the problem. That's why I think we need to move beyond simple reward functions and start incorporating more sophisticated reasoning mechanisms. Maybe something akin to reward-guided tree search, but where the tree itself is constructed by translating the problem into different coordinate representations.
Translate the problem? I like that. It's about reframing the problem in a way that makes it easier to solve. And I think that goes back to my point about the brain's ability to adapt and reorganize itself. It's not just about learning a fixed set of rules. It's about constantly updating your internal model of the world. And that's where I think we can draw inspiration from neuroscience. How can we design AI architectures that are more like the brain, more flexible and adaptable?
Well, that's what the whole field of neuromorphic computing is about, right? Building hardware that mimics the structure and function of the brain. And we're seeing some exciting progress there. Things like spiking neural networks, which are much more biologically realistic than traditional artificial neural networks, are starting to show promise. And because they're so much more efficient in terms of energy usage, it means they can solve larger problems with less power.
But are they truly intelligent, or are they just more efficient pattern recognizers? I'm still skeptical that these bio-inspired approaches are the key to AGI. I think we need to focus on developing better algorithms that can reason and plan and understand causality. And that's where neuro-symbolic AI comes in, combining the strengths of neural networks and symbolic reasoning.
The symbolic and sub-symbolic bridge is definitely important. If you just throw a neural net at the problem, it might find a solution, but it's not going to be a generalizable solution. You need to have some kind of framework that allows you to translate between the raw data and the symbolic representation. And that's where I think the ability to handle different coordinate systems comes in. It's not just about recognizing patterns. It's about understanding the underlying geometry and topology of the world.
Give me an example, Donald. What do you mean by understanding the underlying geometry?
Okay, imagine a robot trying to navigate a room. It could just learn a sequence of motor commands to get from point A to point B. But if it understands the geometry of the room, the walls, the obstacles, the spatial relationships between objects, it can plan a much more efficient route. And if the room changes, it can adapt its plan accordingly. It's not just memorizing a sequence of actions, it's understanding the underlying structure of the environment.
That reminds me of SLAM, simultaneous localization and mapping. Robots use SLAM to build a map of their environment while simultaneously figuring out where they are in that map. It's a classic example of how AI can combine sensory data with geometric reasoning to solve a complex problem. Although I think that pure SLAM doesn't give understanding, just a spatial reconstruction.
Yes, but SLAM typically relies on predefined features and algorithms. It's not learning the underlying geometry from scratch. It's using a set of tools to extract information from the environment. A truly intelligent system would be able to discover those features and algorithms on its own. And that's where I think we need to focus our efforts.
So we're talking about AI that can not only perceive the world, but also understand it, reason about it, and adapt to changes in it. And that's a huge challenge. It requires integrating multiple disciplines, from neuroscience and computer science to mathematics and philosophy. It's not just about building better algorithms. It's about understanding what intelligence is.
But are they truly understanding the text they're generating? Or are they just stringing together words based on statistical probabilities? I still maintain that these models lack genuine understanding and reasoning abilities. They can mimic human language, but they can't think like humans.
I think the LMs highlight the need for metacognitive control. The recent papers on LLMs demonstrating metacognitive control over internal activations is tantalizing. If the LLM can reason about its own reasoning, then it's getting closer. The control of internal activations suggests a degree of structure in the LLM's internal representations, but it still feels like brute force pattern matching.
The implications of metacognitive control are tantalizing, but are not sufficient in themselves. It feels like we're missing a key piece of the puzzle. And I think that key piece is a deeper understanding of how the brain works. We need to go beyond just building models that mimic brain function. We need to understand the underlying principles that govern brain activity. We need to understand how the brain integrates sensory information, motor control, and abstract reasoning.
And that's where detailed, biologically inspired models of the brain come in. We're now able to simulate the neural circuits of the brain with unprecedented accuracy. And by analyzing these models, we can start to uncover the underlying mechanisms that give rise to intelligence. Analyzing these models for emergent intelligence could accelerate our understanding of the underlying mechanisms that give rise to AGI.
But those models are still incredibly simplified. They don't capture the full complexity of the human brain. And even if we could build a perfect replica of the brain, would that necessarily give us AGI? I'm not so sure. I think we need to focus on developing better algorithms that can reason and plan and understand causality, regardless of whether they're inspired by the brain or not.
I think the key is to find a way to translate between different levels of representation. The brain operates on multiple levels, from the molecular level to the cognitive level, and we need to find a way to bridge those levels. A core algorithm needs to be able to translate between different coordinate representations. It's not just about building a better brain model, it's about understanding how information flows between different levels of abstraction.
Okay, so let's think about future research directions. From my perspective, I'm increasingly curious about the role of embodied cognition. I'd like to see more research on how physical interaction and sensory experiences can shape AI learning. What happens if we introduce unexpected physical changes to the AI's environment? Does it learn to adapt to the new physics? Also, the intersection of brain plasticity and AI learning architectures needs more exploration. The potential for AI adaptation is massive.
From my side, I think we need to focus on scaling up deep learning models. We're already seeing incredible results with large language models, and I think we can push that even further. I want to see more research on unsupervised learning in deep networks and on how to efficiently train these models on massive datasets. Also, I'm curious how the brain handles various coordinate systems like visual space, proprioceptive space, and abstract symbolic representations. A unified framework for these different spatial and temporal representations within the brain might provide a blueprint for future AI systems.
I think we need to move away from the purely statistical approach of deep learning and focus on developing better neuro-symbolic algorithms. I want to see more research on how to integrate symbolic reasoning with neural networks and on how to develop models that can reason and plan and understand causality. We should be investigating ways to have AI understand the why behind the outputs and explore aspects of symbolic reasoning to achieve this.
I think we need to focus on the spatiotemporal aspect of intelligence. I want to see more research on how to build AI that can understand different coordinate systems and how to translate between them. I believe a fundamental shift is needed in the underlying algorithm to be able to translate between different representations of space and time. We also need to figure out how to design reward functions that encourage true understanding, not just superficial pattern matching.
Okay, that's a great overview of where we are and where we need to go. It sounds like we all agree that building truly intelligent machines is a complex and multifaceted challenge, and it's going to require integrating insights from multiple disciplines.
Absolutely. It's an exciting time to be working in this field. I think we're on the cusp of some major breakthroughs.
I hope you're right. I'm still a skeptic, but I'm also optimistic about the potential of AI to solve some of the world's biggest problems.
I think we're making progress, but we need to be careful not to get caught up in the hype. We need to focus on the fundamentals and on building AI that is truly intelligent, not just superficially impressive.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We hope you enjoyed the discussion.